In this video, we work our second example involving the method of undetermined coefficients. This is problem number 1 in section 6.3 of Fundamentals of Differential Equations by Nagel, Saff, and Snyder. We've got this third order differential equation and this particular right-hand side. Now, before we start with the method, we should make sure that this method actually applies. Now remember, in order for the method of undetermined coefficients to apply, the corresponding homogeneous equation has to have constant coefficients. So if I made this right-hand side 0, that would be the corresponding homogeneous equation. And notice that the coefficients in front of y triple prime, y double prime, y prime, and y are just 1, -2, -5, and 6. So the corresponding homogeneous equation has constant coefficients. That's our first thing that we need to check off. I'm going to denote that by dE sub h for corresponding homogeneous equation. And then the right-hand side has to be either an exponential function, a polynomial, or a sine or cosine function, or some finite product or finite sum of those. And that's exactly what we have. We've got a second degree polynomial and an exponential function. So the right-hand side is what it needs to be. The right-hand side is the sum of an exponential function and a second degree polynomial. So the method of undetermined coefficients, that's the method where we guess, that's going to work just fine. Because the derivative of an exponential function is an exponential function, and the derivatives of polynomials are lower degree polynomials. So it makes sense to guess that y sub p has the same form as the functions on the right-hand side. So the method of undetermined coefficients, is going to work just fine. Okay, since these are satisfied, let's get started. The first thing that we do every time we're solving a non-homogeneous differential equation is we solve the corresponding homogeneous equation. So I will write that down. The corresponding homogeneous equation is y triple prime minus y, or 2 times y double prime minus 5y prime plus 6y equals 0. And we know how to solve that. Oops. Since the differential equation has constant coefficients, we're going to let y equal e to the mx. Because derivatives of exponential functions are other exponential functions. So if I multiply those guys by constants and add them together, they're all going to be constants times an exponential. And for the right choice of m, all of those will cancel out and we'll get 0 over here. Since it's a third order differential equation, we'll compute the first, second, and third derivative. The derivative of e to the mx is e to the mx times the derivative of the inside, which is another m. And you bring the m down, then you take the derivative of e to the mx again, derivative of e to the mx is e to the mx, times the derivative of the inside, that gives us another m. And then when you take the third derivative, you just get an extra m there as well from the chain rule. If you do nothing else when you're solving a constant coefficient equation, start by letting y equal e to the mx. And then we compute those derivatives. And then we substitute this function and these derivatives into the corresponding homogeneous equation. So our equation after substitution becomes y triple prime, which is m cubed e to the mx, minus 2 times y double prime, m squared e to the mx, minus 5 times y prime, that's m e to the mx. And then we'll add 6 times y, and y was e to the mx. Now, a lot of professors say you can skip this step and go right from this to the characteristic equation. I don't want you to do that because I want to make sure that you actually know where the solution comes from. And the solution stems from this assumption that y equals e to the mx. And we make this assumption again because if I take derivatives of this, I just get constants times exponentials. And if I multiply these guys by constants and then add them together, since they're all going to have the same form, it's a constant times an exponential plus a constant times an exponential, and so on, I could get 0 out of this. So that's why we do what we do, and that's why I don't want you to skip that step. Okay, so you've substituted into the differential equation. Then you want to factor out the e to the mx. So that equation is equivalent to this equation. And an exponential function is never 0, so we're going to have this polynomial function equals 0. Oops, 5. Because it doesn't matter what m is, that exponential is never 0. Okay, so this is our characteristic equation. So we substituted into the differential equation, we simplified. Then we have a characteristic equation. It was a third order differential equation. That means the characteristic equation is a third degree polynomial. So y equals e to the mx will be a solution to this equation as long as m satisfies this equation. Now at this point you want to factor this cubic polynomial on the left-hand side, but it's not 100% clear how you might factor that. If I group these guys together and group these guys together, factoring by grouping isn't going to work. So we've got to try something else. If factoring by grouping isn't going to work, at this point, I would recommend that you try possible rational roots. This gives you some guesses that you can start from as possible roots of this equation. So the possible rational roots of this third degree polynomial are given by the factors of the constant term divided by the factors of the leading coefficient. And the factors of the constant are the factors of 6 in this case. Oops, not plus or minus 6. 6 is the constant term. And the leading coefficient is 1, so we want the factors of 1. Well, we could take 1 and 6 and multiply those to get 6, or we could take -1 and -6. So two factors are plus and minus 1 and plus and minus 6. Plus and minus 2 and plus and minus 3 will also work. And the factors of 1 are plus and minus 1. Now this looks like a fraction and it's got lists in it. It's a little strange looking, but this is just our shorthand for this. The possible rational roots of this third degree polynomial are these 8 numbers in the, like what looks like a numerator of some kind of fraction expression. It's just positive and -1, positive and -2, positive and -3, and positive 6 and -6. And you're taking each of those and you're dividing by plus or minus 1, but dividing by plus or minus 1 doesn't actually do anything. So we get these guys as possible rational roots, and we just need one of them to start so that we can factor out the factor that corresponds to that root. So we're looking for a root, because if we have a root, then we'll have a factor. As I'll show you in just a moment. So these are our possible roots. And now you want to try these. You might be saying, oh, I have to try 8 different numbers. Well, maybe you might have to try all 8, but at least you are not choosing from infinitely many positive m values. Now we're at least down to 8 m values that might work, 8 possible rational m values that might give you a 0 over here. And choosing from 8 is better than choosing from infinitely many. So if you're still thinking that 8 is a lot, I get that, but it's better than infinity or infinitely many possible roots. So I'm going to choose, let's say m equals 1. You're just going to try a value from for m on this list. So if m equals 1, we'll have 1 cubed minus 2 times 1 squared minus 5 times 1 plus 6. So that's 1 minus 2 minus 5 plus 6. And that does give us a 0. So that means m equals 1 is a root of the polynomial. And that means m minus 1 is a factor of that polynomial. And let me just jot down that rule for you again. This comes from this idea that it's a fact. If x equals k is a root of a polynomial, and it has to be a polynomial, then x minus k is a factor of that polynomial. And I'll just label the polynomial p of x. So x minus k is a factor of p of x. That's what I'm applying here. And that's why we were looking for a root. So we had this and we wanted to factor it so that we can find the values of m that cause that to be 0. In order to find those factors, we look for roots. Once we find a root, we've got our first factor. Now, if I know that this is a factor, I can factor m minus 1 out from this. Or alternatively, I can take this guy and I can divide by this, and I'll be left with a quadratic polynomial that we can either factor or solve using the quadratic equation. So that's what we do next. Once you find a root, that's a value of m that gives you a 0, then you want to divide that guy out so that you can factor the polynomial that you have there. Now, if m equals 1 didn't work, we got something that was non-zero, we just go back to the list and try again. So now we're going to divide, and I'm going to call it p of m, p for polynomial, and that is a polynomial in m. We're going to divide it by m minus 1. And we're going to use synthetic division for that. Okay, so my polynomial, p of m, is this guy. And my goal is to factor it. So I'm asking myself, this is equal to m minus 1 times what? Or alternatively, this divided by m minus 1 is equal to what polynomial? Since this is degree 3, this is a degree 3 polynomial, and we're dividing by a degree 1 polynomial, the resulting quotient is going to be degree 2. It's this degree minus this degree. So in order to find this function over here, we're going to use synthetic division. Now, when you're using the synthetic division, you take that factor in the denominator, as long as it's of the form x plus or minus a constant, you take that and you set it equal to 0 and solve for m or x if these were x's instead of m's. So we set that equal to 0. And you solve for m, and we know that that's m equals 1. That's the root that corresponds to that factor. We put that root in the little box. And then the coefficients of your polynomial get listed over here. So we have a 1, a -2, a -5, and a 6. Now, you have to have this written in descending powers of m with no missing powers in order for these to be the coefficients. And this time this is absolutely correct because I've got an m cubed, an m squared, an m to the first, and then there's an implied m to the 0 there. If any one of those was missing, I'd have to add a placeholder. Let's say there was no m squared, I'd have to add a 0 m squared. So you find the value of m that would make this 0, that goes in the box. You list the coefficients over here, and you always bring that leading coefficient down, and then you multiply. That product goes there, and then you add. Multiply and add. Multiply and add. And this should be a 0 if this is truly a root, because that's the remainder. Whatever you get right here is the remainder after dividing. And there should be a remainder 0 if m minus 1 truly is a factor, or alternatively, if m equals 1 is a root, because those are telling you the same thing. So now I know that this divided by this is a quadratic function with these coefficients. So what this synthetic division is telling me is that m cubed minus 2m squared minus 5m plus 6 divided by m minus 1 is equal to 1m squared minus m minus 6. Or alternatively, you can take that cubic polynomial and you can write it this way. It's this times this. So we have m minus 1 times m squared minus m minus 6. And remember, we want this cubic polynomial to be 0. We're trying to find the values of m that make that 0. So I'm still doing that. I'm going to do that on the next page. So we divided p of m by m minus 1. We're finding the quotient. I'll call that q of m. And then you just take your polynomial and you write it as m minus that factor, or m minus that root, times q of m, which is what I did here. I'm just taking this equation and I'm multiplying both sides by that divisor to get this. Okay. So we had m minus 1 times m squared minus m minus 6 equals 0. And we're still factoring. If this factors, we should factor it, and it does. I need two numbers that multiply to give me negative 6, that add to give me negative 1. Since the product is negative, the numbers are going to have opposite sides. So what I'm really looking for is two numbers that have a difference of 1. 2 and 3 will work. If that one's negative, negative 3 plus 2 is negative 1, and negative 3 times 2 is negative 6. So I have a plus 2 and a minus 3 there. So our characteristic equation has been factored, and the only way that happens is if, or the only way this product is 0 is if one of the factors is 0. So either m minus 1 is 0, or m plus 2 is 0, or m minus 3 is 0. So if you add 1 to both sides, you get m equals 1, m equals negative 2, and m equals 3. It was a third degree polynomial, so we've got 3 roots, 1, negative 2, and 3. And then the corresponding solutions to the differential equation are e to the m1x, so that's e to the x, and e to the m2x, e to the negative 2x, and e to the m3x. Okay, so we factored the characteristic equation. You solve for m1, m2, and m3. And then we state the corresponding solutions, y sub 1, y sub 2, and y sub 3. Now we were solving a non-homogeneous problem, so we needed that complementary solution or complementary function. Since it was a third order equation, we get c1y1 plus c2y2 plus c3y3. which in this case is a constant times e to the x plus a constant times e to the negative 2x plus a constant times e to the 3x. Okay, so that is the homogeneous part. Now we want to go back to the non-homogeneous part. So we had this differential equation. Oops, it's not an m, it's a y. Equals that. And now you want to make an educated guess for y sub p based on the form of the right-hand side. Now, we're never 100% sure a guess will work, but often we can tell what won't work and we can multiply by an extra x if necessary so that the functions that don't work aren't part of our solution here. So I've got an exponential function plus a second degree polynomial. So I would guess a constant times an exponential function plus a second degree polynomial. And you don't want just a b times x squared. You want bx squared plus cx plus d. You want the most general second degree polynomial you can find, and that's this one. Okay, now before we try this, we should compare this guess to y sub c. Because remember, e to the x is a solution, e to the negative 2x is a solution, and e to the 3x is a solution of the corresponding, all three of those are solutions of the corresponding homogeneous equation. So if I take any one of those and I substitute into the left-hand side, I'm going to get 0 because they're solutions to the homogeneous equation. Now remember from our preliminary theory, if I take any one of those and I multiply by a constant, I'm also going to get 0. And then if I add them together and I substitute those into the differential equation into the left-hand side, I'm going to get 0 because they're all solutions to that homogeneous equation. So I'm looking at this and then I'm comparing it to this right here to see if there's any part of this that is going to give me a 0 when I substitute it in. I'm fine with the second degree polynomial because there's nothing that looks like a second degree polynomial in my y sub c. There's nothing that looks like a bx squared or a constant times x or a constant by itself. But this constant times e to the x is actually right there. So I can't have a constant times e to the x as a y sub p here. If I substitute that in here, I'm going to get a 0. I'm not going to get a 1 e to the x, which is what I want. So since this is already up here, we say, okay, I'm going to modify this a little bit so that it's not up there. And the way we modify it is we multiply by an extra x. It might seem arbitrary. You might be thinking, why x? And I actually haven't told you why x, but it turns out that multiplying by x usually works. We do this because it works. And we could talk about it in general if we were substituting in general and talk about why multiplying by x will also give you solutions that end up like this. But we're not going to do that. I'm just going to tell you that every time you see this term here and it's part of y sub c, multiply by x until it's not a part of y sub c, and then that should be your modified educated guess for y sub p. Okay. And I will write that differently. I'll write that as ax times e to the x plus bx squared plus cx plus d. That's my y sub p. Okay, now I'm assuming that this is a solution to this third order non-homogeneous differential equation for the right choice of a, b, c, and d. I just need to find a, b, c, and d that make this satisfy this equation. So in order to do that, I'm going to take the first, second, and third derivative and substitute those into the left-hand side, simplify that left-hand side and set it equal to the right-hand side, and then figure out what a, b, c, and d will work so that this side actually gives us this. That's what the method of undetermined coefficients is all about. We're trying to determine those coefficients so that this satisfies this. So we compute the first derivative, the second derivative, third derivative. Now, for y sub p prime, for this first guy here, I need to use the product rule. So I've got a product of two functions. This is my first function and that's my second function. According to the product rule, the derivative is the derivative of the first, derivative of a constant times x is a constant, times the second, plus the derivative of the second, times the first. And then we add the derivative of bx squared, that's going to be 2b times x. The derivative of a constant times x is a constant, derivative of a constant is 0. And before we do y sub p double prime, let's write this a little differently. I'll factor out the e to the x. This gives me an a here, and I've got an ax over there. So this is a plus ax times e to the x plus that polynomial. Now I'm going to use the product rule again. This is my first function, and this is my second function. I guess I didn't quite give myself enough space. It's okay. Let's do that down here. According to the product rule, the derivative of this product is the derivative of the first times the second, undifferentiated, plus the derivative of the second times the first. And then we add the derivative of this constant times x, which just gives me the constant, and the derivative of the constant by itself is 0. So now you've got a times an exponential plus an exponential times this. Let's factor out that exponential from everything. This is y sub p double prime. And I'm left with an a here plus another a, so that's 2a plus an ax. Now let's compute the third derivative. Product rule again for this guy. That's my first function and that's the second function. We have derivative of the first times the second plus the derivative of the second times the first. And the derivative of the constant 2b is just 0. So we'll factor out the e to the x. We have an a here plus a 2a, that's 3a. 3a plus ax times e to the x. If we distribute that, we get the same thing as we get up here. Okay, so we're assuming y sub p is a solution to this differential equation. We've taken the first, second, and third derivative, and now we're going to substitute into the left-hand side and set it equal to the right-hand side. Now to make the bookkeeping a little easier, we're going to add vertically. So I am going to write y sub p triple prime here, and I'm subtracting 2 times y sub p double prime. Then I'll subtract 5 times y sub p prime and add 6 times y sub p here. And I'm going to collect like terms in the columns. It'll just make it easier to keep track of everything. Okay, so y sub p triple prime turned out to be this. So I have 3a plus ax times e to the 3x. And then I'm subtracting 2 times y sub p double prime. So you want to distribute a -2 here and here. So -2 times this is going to give me a -4a minus 2ax times the exponential, and -2 times 2b is -4b. Then we're going to take y sub p prime and multiply by -5. So we're here. So this times -5 is going to give me a -5a minus 5ax times the exponential. And then -5 times this is going to be a -10bx. I don't have an x term, so I'll add that over here. And then I've got a -5 times c is going to give me a -5c. Now I want 6 times y sub p, and remember our initial guess for y sub p was right here. So I need 6 of these. So I need a 6ax e to the x plus 6b squared plus 6cx plus 6d. So I had a 6bx squared. There's no other x squared term, so I'm putting my own column in over there. Then we had a 6cx and a 6d. When we add all of these together, we end up with, well, there's 1ax minus 2a minus 5a plus 6a. So this 1a plus 6a is 7a. 7a minus these two together, that's another 7a. Those are going to be 0. And then over here, we end up with a negative 9a plus 3a, so that's negative 6a times e to the x. And then our constant term is negative 4b minus 5b plus 6d. And then you've got a constant times x here, negative 10b plus 6c times x, plus 6b times x squared. And that has to equal the right-hand side of the differential equation, which was e to the x plus x squared. So I've got 1 e to the x, and then I've got 1x squared, and I don't have a constant term, so I'm just going to add in some placeholders. So that's a 0, and that's a 0 times x. Now, constants, x to the first, x squared, and e to the x are all, they form a linearly independent set. These functions are linearly independent from each other. So that means that the left-hand side of the equation equals the right-hand side of the equation if and only if the coefficients are equal. Because the function here that we're talking about, and the function here that we're talking about, and the function here that we're talking about, and the function here that we're talking about, even though there's just a 0 there. Like those are all linearly independent from each other. So that means the only way these can be equal is if the coefficients are equal. So negative 6a must be equal to 1. And that constant term, negative 4b minus 5c plus 6d, that must be equal to 0. And negative 10b plus 6c, that must be equal to 0. And 6b must be equal to 1. So I ran out of space on my paper here, but I've got 4 equations with 4 unknowns, and these two are really easy to solve. So we can use this to find A immediately. We can use this to find B immediately. And once we have A and B, we can use B to find C here. And once we have B and C, we can use B and C to find D. So according to this equation, A must be negative 1/6. According to this equation, B must be positive 1/6. And then we'll substitute B equals 1/6 right here, and we'll solve for C. And I'll do that on the next page. So we have computed the first, second, and third derivative. We have substituted into the non-homogeneous differential equation. And you're going to set the left-hand side that's simplified equal to the right-hand side. And then we say this equals this if and only if the coefficients are equal. So set coefficients. I'm going to say appropriate coefficients equal to each other. Hopefully you know what that means. When I say appropriate coefficients, that means I want the coefficient of e to the x on this side to equal the coefficient of e to the x on this side. I want the constant term on the left-hand side to equal the constant term on the right-hand side. I want the constant that's multiplying x here to be equal to the constant that's multiplying x here. And I want the constant that's multiplying x squared over here to equal the constant that's multiplying x squared over there. So we've got 4 equations with 4 unknowns, and then we solve those 4 equations with 4 unknowns for A, B, C, and D. So we have A equals negative 1/6, From this equation, we have b equals 1/6. From this equation, we can see that negative 10 times b, so that's going to be a negative 10 over 6, plus 6c must be 0. Now this will simplify. The 2's reduce. Let's add that guy to the other side. And then we'll divide by 6 or multiply by 1/6. That's equivalent. Yes, those operations are equivalent. Sometimes I want to be very careful. I'm like, should I be using the word equal or should I be using equivalent? Language matters. Sometimes I'm not as good at language as I am with all this algebra stuff. See, I still use words like stuff. That's okay. So we've got A, we've got B, we use this equation, we use the value of B to find C, which ended up being 5 over 18. And then next thing we want to do is use B and C here to find D. So we know that B is 1/6, so this is going to be negative 4 times 1/6, or negative 4/6, minus 5 times C. So minus 5 times C is going to be 25 over 18 plus 6D, and that equals 0. Now we just need to solve for D. Let's multiply by 3 over 3 here. So I've got negative 12 over 18 minus 25 over 18. So that's negative 37 over 18 plus 6D equals 0. Let's add the 37 over 18 to both sides. And then we'll divide by 6 or multiply by 1/6, same thing. And we get this, 37 over, we get 60 plus 48 is 108. Okay. You found A, B, C, and D. So we solve the system for those constants, A, B, C, and D. And what that is telling us is that when A equals negative 1/6, then B equals 1/6, then C equals this value, and D equals this value, this function satisfies that differential equation. So now we want to substitute the values that we found, A, B, C, and D, into the form of that particular solution, y sub p. So y sub p was A times x times e to the x plus b times x squared plus c times x plus d. Now, provided I didn't make any differentiation mistakes or arithmetic mistakes, if I take the derivative of this 3 times and substitute into the left-hand side and simplify, I should get e to the x plus x squared. Okay, now, if you've got y sub p and you knew y sub c, you're ready to state the general solution. So the general solution is y sub c plus y sub p, and y sub c turned out to be c1 times e to the x plus c2 times e to the negative 2x. Trying to find my y sub c. It's been a while since we found it, isn't it? Or it has been. There's the rest of it, plus c sub 3 times e to the 3x plus this function. And this is going to work for all real numbers. Now, if you just wanted to see how to solve the problem, you can stop watching here. But I would like to verify for those students that are curious that this actually satisfies the differential equation. Now, I don't think I'm going to verify that the general solution satisfies the equation. It's just going to lead to a lot more differentiation. Not that that's hard, but with 7 terms, it's just kind of tedious. I would just like to prove to you that this y sub p actually satisfies the equation. So I'm going to check that now. Let's check or confirm that y sub p satisfies, I was going to say that differential equation. I'll just say the differential equation. So we have y sub p equals, I'll say y sub p of x equals this. 1/6. Those transcription errors, those will get you. Okay. So in order to see that it satisfies the differential equation, I need to take the first, second, and third derivative because it was a third order differential equation. So according to the product rule, this is my product. We get the derivative of the first times the second plus derivative of the second. This is my first function and my second function times the first. And then you have a 1/6 there. And the derivative of x squared is 2x. Derivative of a constant times x is just the constant. And this simplifies. We end up with negative 1/6 minus 1/6 times e to the x. I'm factoring out that e to the x from both of these guys. And then 2 times 1/6 is 2/6, which is the same as 1/3. Okay, second derivative. Let's do it again. First function and our second function. According to the product rule, the second derivative is derivative of the first times the second undifferentiated plus the derivative of the second times the first. So that's that product rule, and the derivative of this constant times x is just the constant. The derivative of the constant is 0. Now, if I factor out that e to the x, I've got negative 1/6 minus 1/6. That's negative 2/6 or negative 1/3, same thing. So that's right there. And then y sub p triple prime, take the derivative again. I'll call this my first function and this my second function. We have derivative of the first times the second plus derivative of the second times the first. And if you're a student and you're thinking, oh, Miss Townsend, why do you keep doing that? I'm doing that because it helps you remember. And it helps me remember. It helps everyone remember. And most people need a little refresher. But by the end of the semester, you'll know all the differentiation rules that you need to know. And then when you go to the big university, you will know what you're doing when you get there, which will be a wonderful thing. Okay, so we factor out the e to the x, and we've got a negative 1/6 here, minus 1/3, or that's negative 1/6 minus 2/3, or 2/6, excuse me. So minus 1/6 minus 2/6 is going to be minus 3/6, or 1/2, negative 1/2. And then we have that negative 1/6 x there. Okay, so we took the first, second, and third derivatives of this function, and then we want to substitute those into the left-hand side of this non-homogeneous differential equation and show that we get e to the x plus x squared. Now, I actually have not checked this myself, so I am hoping and praying that my algebra was correct. I'm pretty sure my calculus was fine, but sometimes we make a little arithmetic error, so, or a transcription error, just writing down a 2 instead of a 3 or something like that. So hopefully I didn't do that this time. So we're going to substitute into this and hope that we get e to the x plus x squared. These are our derivatives. Okay, so the left-hand side of the differential equation was y sub p triple prime minus 2 times y sub p double prime minus 5 times y sub p prime plus 6 times y sub p. And we're taking each of these right here, and then we're going to add, and I'm adding vertically just to help with the bookkeeping. So y sub p triple prime is negative 1/2 minus 1/6 x times e to the x. And then we're subtracting 2 times y sub p double prime. So we want to take this and multiply by -2. -2 times -1/3 is positive 2/3. -2 times -1/6 is positive 2/6, which is positive 1/3 times x. Maybe I shouldn't simplify. Maybe it'll be easier to do the arithmetic if I don't simplify. I think I will. Well, we'll see. I'll keep simplifying as we go. And then we have -2 times that 1/3 there is going to give me a -2/3. Now I want to take y sub p prime and multiply it by -5. So -5 times this is going to give me a positive 5/6 plus 5/6 times x times e to the x. And then I'm taking this guy and I'm multiplying by -5. So I've got -5/3 times x there. And then I want this guy times -5. So that's -25/18. And then I want 6 times y sub p. So this times 6 is just going to give me a negative x times e to the x. And that's a 1/6 x squared times 6 is going to give me an x squared. And then this times 6, well, that 6 goes into the 18, excuse me, 3 times. So we'll have plus 5/3 times x from that. And then this one times 6, we do the arithmetic on the side. This is 37/108. And 6 goes into that how many times? 6 goes into 10 once, and then it goes into 48 8 times. We're multiplying by 6, so we get 37/18. Okay, now here's hoping that all of my arithmetic is correct, and when I'm done, I get e to the x plus x squared. If I do, that means that the entire method was correct. It led to the right answer, and then I didn't make any mistakes when I was finding the coefficients or checking my answer. So let's see if we get what we're supposed to get. Okay, so I have a -1 here and a -1/6. So that's -7/6, right? And then here, this is 1/3, which is the same as 2/6. So I've got 2/6 plus 5/6 is 7/6 minus 7/6. So that's 0. That's good. And then here, I guess I need these to be 6 as well. I've got -3/6 plus 4/6 is 1/6. 1/6 plus 5/6 is 6/6. So that's a 1 times e to the x. Excellent. That's exactly what we needed on the right-hand side. Over here, I've got an x squared. That's also excellent. Now, this should be 0 and this should be 0. -5/3 x plus 5/3 x is 0x, so those are gone. Awesome. And then here, well, these guys I can combine. This is going to give me a 12/18. And 12/18 is 6 times 2/6 times 3. So the 6 is reduced, and that's 2/3. So this is 2/3 minus 2/3. That's 0. So when we substitute y sub p into the left-hand side, we get the right-hand side. Where is it? So many pages ago. Here's my differential equation. This is the one I'm looking to solve. So I know my y sub p is correct. Now we could just as easily check these functions, substitute them into the differential equation, and show that we get 0. And then we could also take these guys and add them to the y sub p and differentiate 3 times and show that we get e to the x plus x squared. I'm not going to do that, but I just wanted to show you that's what we're doing. This actually works. When you're done, you find a function that if you took the derivative of this 3 times and you substituted into the equation, you get the right-hand side.